About a year ago, I did a comparison, or actually closer to 2 years ago, between these two spectrum analyzers. On the top is an Instek GSP-730, and on the bottom is the Rigol DSA-815. The comparison was done with the idea of suitability for a graduate or undergraduate communications lab in electronic engineering. And so while that is different from most laboratory or industrial applications, and certainly quite different from amateur radio, which I'm also an amateur radio operator, I thought I might put some of those results in the form of a video comparing these two. And the way I'm going to do it is I'm going to use a set of experiments that Instek produced for an RF and communication trainer, which you may see right there. And I'm then going to run both instruments on those experiments and see, trying to assess ease of use and specs and things like that. Now, what I have on the screen right now is a local FM broadcast stations. The span is from about 85 on the left to about 110 megahertz on the right. So what I'm going to do now is I'm going to set up the trainer down here to do some of the experiments that are in this book by Instek, which, by the way, comes with the trainer. So the first experiment that we're going to do is demonstrating basic operation of a spectrum analyzer, and for that we're going to be looking at a start and stop frequency, which in the book is 800 megahertz to 1.9 gigahertz. Well, the problem is that the GSA-815 won't go to 1.9 gigahertz. So I'm going to change this for both units to 1.5 gigahertz. This is the result of using the antenna that comes with the Instek unit and setting the parameters to 800 megahertz start frequency and 1.5 gigahertz stop frequency, minus 40 dB reference level. And you notice there are several signals displayed there. Now let's go over to the DSA-815 with the same settings and see what we get there. Now here is the DSA-815. You may notice the start frequency 800 megahertz, stop frequency is 1.5 gigahertz, and the reference level is minus 40 dBm. I think that's up here in this corner. Yeah, right there. And the reference level on this one was minus 40 as well. And all I've done, I moved the antenna from the Instek down to the 815. And you may notice there does not appear to be any signals there. I don't know exactly why that was true. I haven't tried this experiment on the Rigol before. It worked so well on the Instek that I never had any reason to believe that it wouldn't give you the same signals on the Rigol, but this is one place where there's an obvious difference, and I can't believe that it's sensitivity. So I'm going to check around and see if there's something that I may have set differently on the DSA-815. I was puzzled why the Instek seemed to be a lot more sensitive than the Rigol in the frequency range from 800 to 900 megahertz. That is part of the cell phone band, and there even are some old wireless cordless phones that work in that same frequency range. But I think I have figured out what's going on. At first, it turns out that the Instek is pretty sensitive, particularly near the higher ends where the Rigol runs out, of course at 1.5 gigahertz. But I've discovered that the Instek has pretty flat frequency response all the way out to about 3 gigahertz, based on some measurements I've done using the HP generator over there, which will go to 2 gigahertz. It won't go all the way to 3, but over the range of that HP instrument, which is very accurate and very flat, the Instek works very, very well. I'm happy to report that the problem that I was having with the Instek being insensitive in that region, I was able to solve by first, the unit comes up with 10 dB of attenuation, and so I removed that attenuation. In other words, I set the input attenuation to 0 dB. Then I turned on the RF amplifier, or preamp. You'll notice it's right there. Doing that brought out the 800 to 900 megahertz. I think the center frequency is about 850 here. 800 on the left, 900 on the right. So at any rate, as you can see from this one and from this one, they are both equally sensitive if you turn on the preamp for the Rigol. In other words, if you set the Rigol to its most sensitive range, or its most sensitive input, then it produces roughly the same spectrum that the Instek does. So I'm making this video later than the others, and I'll insert it into the video so that people who are thinking of buying one or the other won't be misled. You can get the same results on the Rigol. Just take out the input attenuation and turn on the preamp. And of course what I'm doing here is I'm just using an antenna. And in this case, I'm splitting the antenna, and I realize there's a mismatch there, but since the antenna probably doesn't, if you were transmitting, this would make a difference, but for receiving, splitting a 50 ohm antenna into two 50 ohm inputs is certainly acceptable for these kinds of tests. In doing the earlier videos, reviewing them, I realized that in my haste to get on with a number of experiments, I may have kind of glossed over the characteristics of this RF trainer. And while there's plenty of stuff on the internet and YouTube and so on with regards to things like the DSA-815, in fact N2CUA did a whole series of experiments with that a couple of years ago, and the GSP-730, there's a bunch of videos on there that were done by an Instek engineer, but very little about the RF trainer. And since it's kind of the heart of what I'm doing here, I thought I might talk about it just a little bit. Now first, I'll point out that I think there are at least 3 models of this RF trainer that are out there, and I think I have the second model. The reason that I say that is, this is a picture of, printed from the manual that came with my unit. And it's apparently an earlier version in which you may notice right here, there is a ground symbol and a test point for a ground. Well, my unit does not have that, and the new manual that I downloaded from the Instek website just a week or so ago, it doesn't show the ground either. In fact, because there was no ground, I added a grounding point to mine. Here are the specs. You may notice that it has 3 parts. It has a baseband, it has an RF FM section, that is a VCO, and then it has an AM modulator. Now, the unit will produce three kinds of baseband signals from about 0.1. I say about because it turns out that the frequency synthesizer in this is not really very accurate. But anyway, from about 100 kilohertz to 3 megahertz. The triangle, it says, won't go that high, but I think that's actually incorrect because I've been able to get a triangle that here you see is a 2 megahertz, and you may notice it's the middle LED that's lit up, the triangle LED. And up here on the Tektronix oscilloscope, you'll see, is a 2 megahertz triangle. See, there's the frequency 2 point, well, and you see it's jumping around. Now that could be the scope failing to correctly do that. But nonetheless, this is not an especially good synthesizer. It's just really intended for training purposes. So that's the basic unit. The basic unit has a baseband that is this up to 3 megahertz. It will do three kinds of waves. It has an output here and a test point here. These are wired in parallel. It has a synthesizer that runs from about 880 megahertz up to, I think, just about 900. It has three test points, and we'll talk about those a little later. You can set the frequency here. And then it has an AM modulator where you input the AM signal here, the RF signal here, and you get a modulated AM signal out here. Of course, if you want FM, you put your signal into this input, and it basically frequency modulates the RF synthesizer's output. So here is something that I copied out of the manual for this. Basically shows how this works. It has a CPU and fundamentally a voltage controlled oscillator with a phase detector, low frequency filter, low pass filter, and feedback, and it's just your typical phase lock loop. You can also put in an FM signal. It's shown down here, but I've relabeled it here because actually this shows the baseband connected to the VCO, and the only way you can really do that is to put it into the FM in jack. In addition to the FM capability, it has an AM modulator, and I'll show you that one here in just a second. The AM modulator is fundamentally a diode mixer that over here is the AM in. There's a relay that allows you to switch the signal, and then you have a balanced mixer with a 5-volt DC offset. And I assume the reason that they did that was so that they would get a symmetrical signal around ground. So you put the RF in through there, you put the AF in through here, and you get the modulated signal out at this point, which is one side of the bridge. Now this, the reason I have these schematics is because when I first got this unit, the square wave did not work. And I sent it back to Instek, and they worked on it and sent it back. I thought they had fixed it, but it turns out they had not. I later found the problem, but in the interchange with Instek over the problems with this unit, I got a hold of one of their engineers, and eventually, rather than have me send the unit back, I think I convinced him that I was knew enough about electronics to work on the unit. So he sent me the schematics for this GRF-1300. I don't think they're normally available. On the screen is a DSA-815 display of a 1 megahertz sine wave. The sine wave is generated by the GRF-1300. You see on the left where it says F1.00, and then the signal comes up to a BNC splitter and then goes up to the DSA-815 there. I'm going to use this 1 megahertz comparison to lay some groundwork for understanding how to use spectrum analyzers. On the screen there you see with a little peak at the top, the sweep is in yellow, and at the top there's a marker that marks the peak. We'll talk about that a little later when we can zoom in a little more and look a little more at what the screen is actually doing. Also, I'm going to defer for a minute the actual setup of the spectrum analyzer. Over here is the 730 with the same display, and I have the span, that is the frequency difference between the left edge of the screen and the right edge of the screen, set to 2.5 megahertz. And the reason I did that actually has more to do with this display, which is the Tektronix 2024 displaying the same frequency in its FFT mode. Now, this illustrates one of the reasons why that spectrum analyzers are much better at this than FFTs. Now understand, an FFT is simply a mathematical computation of what you have on the screen. So if I turn math off, that's the wave that it's actually analyzing. And if you've watched the introduction to spectrum analyzers, the reason that we set it to something like that is many, many cycles before we do an FFT, is the resolution of the FFT is determined by how many cycles of the signal you have in the memory being used for the FFT computation. I refer you, if you want a little more information on that, to watch the video that Alan W2AEW did on exactly this same scope. I think his is a 2104 or 2204, but at a megahertz doesn't matter. And he explains a lot about the relationship between those two. On a spectrum analyzer, there are three fundamentals that I think it's important for people to understand before they set up a spectrum analyzer, because there are trade-offs among all of these various these three factors. Those three factors are the measurement time, or I should say the time per frequency step, the resolution bandwidth, and the span. So let me show you what I mean by all of that, and then we'll come back and actually do some hands-on with these spectrum analyzers. Let's start out by talking about the span. The span is the difference between the frequency on the left edge of the screen and the frequency on the right edge of the screen. So in the example I just showed you, that was 2.5 megahertz. Span is always measured in hertz, or kilohertz, megahertz, gigahertz, etc. The second factor is what's called the resolution bandwidth. The resolution bandwidth is the effective width of the filter that is used in that particular spectrum analyzer. Now that filter can be a physical filter, a multipole Chebyshev or Butterworth in some of the older spectrum analyzers. Modern spectrum analyzers tend to be digital, so in that case it's a digital filter. And basically it determines the width of the area in which you compute power. Now, a spectrum analyzer doesn't actually measure amplitude of the signal. It measures the total power within a particular resolution bandwidth. The third thing that is a factor is the sweep time, the length of time it takes to go from the left edge of the screen to the right edge. And at some point in the future, if we ever talk about using an oscilloscope, for example, to trigger a spectrum analyzer, this becomes really important. But for now, I'm going to defer sweep time, except it's just the length of time it takes the sweep to go from the left edge to the right edge. There is an amount of time from the time that the filter settles at its position until the output of the filter is stable. And that is called settling time. It's the time from when the switch is made until the output of the filter becomes stable. Then there is a time that the ADC, the analog to digital converter, has to operate before it accumulates enough data to determine the power in that particular bandwidth. And that is called the measurement time. And it's determined by the kind of ADC you use. If you use a faster ADC, then the measurement time goes down. There also are ways you can get faster settling time in filters. Unfortunately, the faster the settling time, generally the less well behaved the filter is. And that is a major factor. Now, with digital filters, fortunately, you can do a lot of things you couldn't do with physical filters, and that helps a lot. But the total time from when you change resolution bandwidths until a measurement is ready, and therefore you can move on to the next resolution bandwidth, is called the time per step. The modern spectrum analyzer sets the frequency to the left-hand edge, opens a bandwidth filter, and samples the power. When it has made an accurate measurement, or when the time per step has extinguished, it steps to the next one and measures that, and so on. Now, I have this shown with somewhat coarse resolution bandwidths. Of course, in a normal spectrum analyzer, these would be very, very tiny relative to the total span. The time it takes, that is the sweep time, from the left side is determined in part by the characteristics of the filter and also by the characteristics of the analog to digital converter. By the time it has stepped all the way across the span, you have gathered the power in each of these resolution bandwidths. So let's look at that on a spectrum analyzer. On the left, you see the center frequency, the resolution bandwidth, which in this case is 30 kilohertz, the video bandwidth, which we talked about in the introduction, but I'm not going to go over at this point. Then the span, which in this case is 2.5 megahertz. Well, I think that has changed. It looks like it's 2 megahertz. And the sweep time, 10 milliseconds. So at a resolution bandwidth of 30 kilohertz, it takes the Rigol 10 milliseconds to cover a span of 2 megahertz. Now on the Instek GSP-730, you notice that the resolution bandwidth is 30 kilohertz. The span in this case is 2.5 megahertz. I think I made a mistake on the Rigol. But notice the sweep time. It takes 1.5 seconds for this spectrum analyzer to complete that 2.5 megahertz sweep. Now I've changed the center frequency to 5 megahertz and the span to 10 megahertz. So 5 megahertz is the center. 4, 3, 2, 1. This is still our 1 megahertz signal, and you notice there are some harmonics. Even though this is supposed to be a sine wave, and if it were a pure sine wave, it would only have this one megahertz signal. You notice there's a second harmonic and a third harmonic. Let's now change the wave to a triangle and watch what happens to the spectrum. You'll notice that the second harmonic, fourth, sixth, and so on don't get very much bigger, although some of the higher order second harmonics do get a little more prominent. But the main thing is that the odd harmonics, that is the third, fifth, seventh, ninth, get quite a bit more prominent. Now let's go to a square wave, and you'll notice with the square wave, not only do the odd harmonics become even more prominent, but the even harmonics, second, fourth, sixth, and so on, become prominent. On the Instek, and as we had on the Rigol, on the far left is the 1 megahertz sine wave, but let's now go to the triangle wave, and you notice once again that the odd harmonics become prominent. Go to the square wave, and both the odd and even harmonics become prominent. Now we'll go through the same sequence of sine, triangle, and square wave on the Tektronix using the FFT. This is the sine wave, and the scope is set up for 500 kilohertz per division, and the reference is 10 dB, that is 10 dB per tick or per graticule. Now let's switch to a triangle wave, and you'll notice how the third harmonic, this of course is the fundamental, first harmonic, or the second harmonic actually, would be here, the third harmonic would be here at 3 megahertz. And now we'll go to the square wave. You'll notice that the third harmonic increases in amplitude, as it should, but the second and fourth harmonics increase in amplitude as well. I found it useful when I first started using spectrum analyzers to fix in my mind the differences between them and oscilloscopes. Some of the differences were a little counterintuitive. For example, on an oscilloscope, generally everything is measured relative to a zero line. That can be ground, or in the case of an AC coupled signal, it can be the average of the signal. But nonetheless, on an oscilloscope, most of the measurements are made from a reference near the bottom of the screen, and the signal moves up from there or up and down from there. On a spectrum analyzer, everything is measured from near the bottom of the screen, but the reference is the top of the screen. It's important to keep that in mind. Later we'll talk about the amplitude key on a spectrum analyzer and how you can use it to set this top line. But if you first keep in mind those differences, the second difference of course is frequency, whereas in the oscilloscope it's time. Third is there are multi-channel oscilloscopes, and actually there are some multi-channel spectrum analyzers, although they're very, very rare and very, very expensive. But on the spectrum analyzer, the equivalent of multi-channel on an oscilloscope is multi-trace. It uses the same input, but what it does is it allows you to have more than one display of that input based on differences. So for example, you can have a single trace that is in real time, you can have another trace that is, say for example, a peak hold or something else. We'll talk about each of these at some point, but basically, if you remember that on an oscilloscope, we call it a channel 1, channel 2, channel 3. On a spectrum analyzer, we call it trace 1, trace 2, trace 3. The basic operation of a spectrum analyzer revolves around these three keys. This is the frequency key, this is the span key, and this is the amplitude key. In general, there are two ways that you can enter frequencies. You can enter a start frequency, that is the frequency on the left, and a stop frequency on the right. Or you can enter a center frequency and a span. Obviously, if you know the frequency that you're interested in and the approximate range around that frequency that you want to look at, then using frequency, center frequency and span is a much easier technique. On the other hand, if you want to look at an area of spectrum, for example, if you want to look at the FM band in your neighborhood to see the signals on the spectrum analyzer, it's a lot easier to remember 88 megahertz on the left, 108 megahertz on the right, and that way you don't have to compute in your head what the center frequency is and what the span is. So let's look at both of those. When you enter frequency, on the Rigol, a menu like this comes up, and we'll see in a little bit the same thing on the Instek, which offers a center frequency. You can just enter that I have entered 880 megahertz, and then you hit the span key and you can enter a span. Right now the span is 2 megahertz. I'm going to change that to 1 megahertz. I apologize, I entered 7 megahertz. I do that often on this because I've used the Instek a little more than the Rigol, and the keyboard on the Rigol is upside down from the Instek. The third major key is the amplitude key. When you enter the amplitude menu, it offers to auto scale, and you can press that if you want to do that. I generally recommend you avoid auto scale, particularly when you're learning, because you'll learn a lot more about spectrum analyzers if you actually enter values yourself. So in this case, what it is showing is the reference level. The reference level is the line at the top of the screen. So let's change the reference level, and I'm going to use the up and down keys. That causes it to move in 10 dB increments. So you notice that the trace has dropped by 10 dB. We'll go back up. Now 0 is at the top again. As you, in this case, raise the reference level, the trace will drop. As you lower the reference level, the trace will move up. You also have the option of entering the scale, whether to use a logarithmic scale, which is the typical and default setting, or whether to use a linear scale. You also can use different units. This is dBm, that's the default. You can also have dB volts, dB microvolts, however you want to measure this within I think in this particular Rigol, it has like 4 or 5 different measures that you can use. And finally, you can also change the scale of the screen. The normal screen has 10 dB per reticule, per square in other words. But you can make that 5, just like on an oscilloscope. You can adjust the volts per division. On a spectrum analyzer, you can have 10 dB per division, 5 dB per division, 2 dB per division, or 1 dB per division. So now let's move on and measure this signal and then look at the same thing on the Instek. In order to measure the phase noise at several different frequencies, I'm first going to change the span back to 2 megahertz for reasons that you'll see in a little bit. Then I'm going to go to the peak function, which identifies the peak with a little marker, number 1 you see at the top, and on the left you see the dB level. It shows that this is at minus about 5.5 dB. On the Rigol, you can do a phase noise measurement fairly easily. Once you have set a marker, if you go to marker function, you will notice that there is a menu item for noise marker. If you press that, the marker changes to measure the noise level. In this case, it is minus 49 dBm per hertz. We'll talk a little more about why it's done in that manner, but to give you an idea of what it's doing, it's measuring the difference between the power at the peak, in this case where the marker is, and the noise level down here. And it's displaying that as the noise marker. Now we'll go over to the Instek and we'll do somewhat the same thing, but we will discover that for various reasons the process on the Instek is different. On the Instek, we set up the same settings, that is a reference level of 0 dBm, a center frequency of 880 megahertz, and a span of 2 megahertz. On the Instek, to do the same phase noise measurement, however, you have to use a feature called a delta marker. I'll show you how to do that in a minute, and then you have to plug the values in to a formula to compute the actual phase noise. So it's less convenient. However, this is the more general method, and it's the method you normally use. Once again, we'll do a peak search to find the peak of the waveform, and just as on the Rigol, you'll see the little number 1 at that point. Now we will enable the marker menu, and we will change the mode from normal to delta. The delta marker requires that you offset one from the other. In our case, I'm going to use 500 kilohertz of offset. On the screen, you see the delta marker showing a difference of, it moves around, it's as low as 37 and as high as 48 dBm. The delta marker in this case is at this point. You see the small white symbol there. And at that point there's a lot of noise. Unlike the Rigol, there's quite a bit of noise in this area near this frequency spike. That is a characteristic, an unfortunate characteristic of the Instek. It has a lot of phase noise near its center frequency, a lot more than the Rigol does. In fact, in the specifications, Instek deliberately specifies their noise level out here on the edge. So once again, we get levels. Right now it's reading 45, and of course that will change if I increase the offset, the delta offset. Let's go to 700 kilohertz, and now the offset is 54 dB. That is the difference between the delta marker value and the peak of the wave. In the student manual, Instek provides this formula for computing the phase noise. Enter the difference between the peak and the delta marker values, which at this time is 54 dB. You then subtract the log of B. What's going on there? You may remember that when you divide something using logarithms, you subtract. What that is dividing the screen up into individual 1 Hertz segments. So you take the resolution bandwidth, you determine its log. Remember, these powers are in logs. You subtract the log of the bandwidth. They adjust the bandwidth to 1.2 times the resolution bandwidth. That's peculiar to this particular spectrum analyzer. Other spectrum analyzers will have a different factor, but nonetheless, it has to do with the skirt shape of the filter they're using. You determine the effective bandwidth, plug it into this formula, take the log of it, and that chops the screen up into 1 Hertz segments mathematically. In case that last explanation was a little cryptic, what I was trying to say is that if you look at this diagram, remember that what a spectrum analyzer is doing is it's measuring the total power within its resolution bandwidth. In the case of the resolution bandwidth that I was using on the Instek and the Rigol, that was 30 kilohertz. So it's the total power within that 30 kilohertz, divides it by 30,000, 30K, and that gives you the power per hertz. That is how you would compute phase noise using a delta marker. By the way, this same formula will work for the Rigol, and in a minute we'll come over and use a delta marker on the Rigol to compute essentially the same thing. Now we're back on the Rigol DSA-815 with exactly the same trace and exactly the same span and center frequency. In this particular case, I have displayed the marker menu, which is the menu that shows when you press the key here called marker. You will notice that right now normal marker is highlighted. I'm going to press delta marker, and then I'm going to offset the delta marker to 500 kilohertz. And here you see the phase noise on the, the level at the delta marker with the 500 kilohertz offset. It's reading right at, in the high 60 dB level. So once again, you can plug these same values into the same formula. What I've done now is I have applied the same signal to both spectrum analyzers using a T, which is shown there. What that does, of course, is it divides each signal into half as much power, or another way to put it is it reduces each signal by about 3 dB. I'm going to use this method going forward so that you can see the screen of the Rigol and the Instek side by side. But realize that you normally would not do this, and if you do this, you have 3 things you have to account for. One is that there may be spurious signals generated in the input of one that will then be cross-coupled into the other. The second is you are reducing the effective level by 3 dB on each instrument, and finally you are introducing additional noise and reflection. Now I've switched the input, still divided by the T, but instead of coming from the Instek trainer, it's coming from this HP synthesizer. Now let's look, though, at the differences. I've adjusted the HP to be the same frequency, and you'll notice now the 500 kilohertz noise level relative to the center is at about minus 62 or 3 dBm. Similarly, On the Instek, a delta value of about 53 or 54 dBm. So you can see that not only is the HP generator generating less total noise, in other words, once again, you're still limited in how much you can measure on the Instek relative to the Rigol because the Instek has a higher noise floor. So this about concludes the basic spectrum analyzer measurement, that is measuring a single frequency and calculating or measuring its phase noise. Next, I'm going to move on into modulation and other issues, but I'm going to do that in the next part of this video. So this will be the end of part 2.